steep. I never really know until I'm halfway through it. So keep an eye on my mistakes because they are bound to present themselves. Poisson distributions, they look like this. So e to the minus lambda, lambda x over x factorial. So I might call that the probability of x given lambda. So it's a mass function. We covered that last time. And so if I have xi's in here, we need to do it. We need to label everything. So let's just write down the likelihood for lambda. It looks like this. I goes from 1 to n, e to the minus lambda, lambda xi over xi factorial. This is the first part of being a Bayesian that I really enjoy. I get to get rid of that right there, the xi factorial, which in my universe, that's a nightmare to compute. So let me just ask you guys real quickly, how big of a factorial can you compute on your computer and have any confidence that it's actually the number that you're asking for?
Less than 30. 50.
In my day, it was like 52, bless you. So in single precision, it's like 52 factorial. So pretty small numbers. You know, if you saw 152 factorial, that would bust up your computers. And you'd have to start approximating that number. So there are approximations. I get really weary when people say I approximated something and they don't show us how much it actually matters and tell us precisely. I don't like it when people start to say, well, as n gets big, it doesn't matter. Because we've already seen a lot of problems where n's getting pretty big and it's not good enough. So it's very context specific. I love just not having to compute that thing. This is pretty easy to work with. E to the minus n lambda. Lambda to the sum of the xi's. I goes to 1 to n. And then I start looking at this thing and I start thinking, what could I multiply this by such that it would preserve the form of that thing I'm multiplying it by? And you probably can instantly recognize this looks like the kernel of a gamma. So if I multiply gamma into it, it'll still look gamma, which is kind of cool. Keep in mind, in terms of x, this is Poisson, which is an entirely different creature. But in terms of lambda, it looks very gamma-ish. And so that would be your first indication as to what the conjugate prior is. I don't know of any other game for recognizing conjugate priors. If you don't know what the distributions look like, you'll never recognize them. How do you recognize something that you don't know what it looks like? So, but this is pretty easy because we've already learned about gamma. And so I'm thinking pi lambda is equal to a gamma. It's got two hyperparameters, alpha and beta. And this thing is proportional to alpha, or I'll say lambda to the alpha minus 1 e to the minus beta lambda. And I might throw in the normalizing constant into all of this. What does it look like?
Beta to the alpha.
Which one?
Beta to the alpha.
Beta to the alpha.
Right.
Alpha minus 1 factorial. We might see that again in a moment, but that's gamma alpha. And so for the problem that we're studying with the posterior predictive distribution, it might be useful to recognize what these things look like. So that normalizing constant, we're going to use it twice. So, but that's what it looks like. For the inference game, all we need to do is recognize this. Keep in mind, something else to remind yourself, like integrate over something that looks like that, I get the inverse of that. And something to remind yourself is beta to the minus alpha and all the problems we've touched before, looks like a t distribution. So something just to remember. But let's end up just coming up with our own theory. I'll write it like that. This is going to be proportional to lambda to the sum of the xi's plus alpha minus 1. Don't absorb that minus 1. You're going to use it to recognize which gamma this is. This is e to the minus lambda n plus beta. So don't forget n. If n doesn't appear in your problems and you're not indexing all your xi's correctly, That would be a big blunder on midterm. So if you think that answers don't have something to do with n, they usually do. So you want to see that here. So the common mistake I sometimes see on midterm 1 is somehow there's just one xi here that appears, and n doesn't appear right. Be careful with those. They should always appear. You always want all your xi's coming into the problem, into your inference, and you want to see n. So this looks like a gamma. The appeal of a conjugate analysis, we're just updating our parameters. So we started with these parameters, and then in a conjugate analysis, effectively you're just updating the parameters. The distributional form is staying the same. That's what it means to be conjugate. Where this is alpha tilt, and this is beta tilt. So we could also look at a few things. Expectation of lambda given x. See if any of this stuff makes sense. That's going to be alpha tilt over beta tilt. So those forms that we know. We could also check the variance in a second if we wanted to. So this is just equal to sum of the xi's plus alpha over n plus beta. And we recognize this thing. It kind of looks like x bar. And as the xi's is and it's increasing, that thing is increasing. And it starts to overwhelm that. And we can get a sense of how the alpha and betas are applying weight to this problem. They're kind of like acting like a data point in there. And so if you're trying to explain to somebody how much weight that was worth in this linear expression, you could probably tell us exactly what it's worth. And you can even see it down here as well. So this is acting like a data point. We probably want alpha and beta to be the same. So basically, we don't want to bias the problem. So move that mean around. So if alpha and beta are the same, then on average, what I'm multiplying by in the conjugate prior is something that's on average 1. So that's kind of nice, which is going to shift where the modes are of this problem. This converges to the mean if alpha is equal to beta, and that's going to 0. You could just set them equal to 0 if you'd like, but this has an appeal that I don't actually have to think about this prior being improper. You can probably just in your mind figure out that it's improper, but when alpha and beta are 0, this thing, if I just plug the alpha and beta into here, this just looks like 1 over lambda, which is improper. Improper. So same prior that we've seen before. And this might have appealed to you a while ago if you were thinking of lambda as a scaling parameter, and that's the way that I tried to explain it last time. So it's just an interesting fact that it's also the mean, but I think of it as scale. This please.
Is that equal alpha and beta equals 0? No.
Alpha equals beta, and it's going to 0.
Okay, it can't be 0, okay.
I mean, I said it equal to 0, but I'm giving you a different way to think about it. You don't have to think about it exactly being 0, and think about this thing being improper, but you can think about what happens as it goes to 0 and it converges to this posterior. So people that don't like to think about improper priors like to think about them as limits, as to what is this limiting distribution looks like as I become more and more improper. This is the limit of that process. This is proper posterior, and that's the key point. So that's pretty easy. We could do the same thing with variance. What does variance look like? Alpha tilt over beta tilt squared. So you could work through that. Want to remind ourselves what these things are because you might use them in the future. So that's just important. You can plug in what those numbers are. I don't think that there's any great insights. My friends usually don't know much about variances to begin with things, but they like to think about means. So sometimes I like to think about the mean just as a sanity check. What is this? Where is it placing mass? Does that seem right? Just real quickly, for this problem right here, what is the MLE? It's X bar. How did you do it? You can see it. How it's going to play out. My guess is you've done it before. So you took the likelihood, you took a log of that likelihood, you took a derivative with respect to lambda, you solved for it equal to 0. So the MLE is this X bar. So we're getting a very similar sort of result that we saw in the beta distribution, the beta binomial problem, is that it's converging to something that the frequentists like to talk about, but there's a little bit of penalty weighted here, and very often people take alpha and beta equal to 0. And you can think about all that scaling variance stuff again. So we've got a couple reasons that are building up for preferring this prior. If you know how to say anything about this prior distribution, you know how to say just as much about the posterior distribution. So that's appealing as well. Let's do the prediction. So we might want to predict x tilde given x. So predict the future. This is our notation for that random variable, x tilde, and this is our past. x1, xn, that's what we've seen. And so what does a Bayesian want? They want the distribution of this quantity. So this is how a Bayesian thinks. So conditional on the data, you're conditioning on the data, you're saying something about your unknown, and you're going to put a probability distribution on it. That's a Bayesian. Always a Bayesian. So you can always tell a Bayesian from a non-Bayesian just by the way they set it, where they place the probability mass. Place it on the unknown and fix the data, that's a Bayesian every single time. So we want this thing. And this is going to be equal to integral fx tilde, I'll call it PR tilde if you like, given lambda. It's just that distribution, but it has an x tilde put in. And this is going to be the posterior distribution that we just solved for. So that was pi lambda given fx. So we're just going to integrate against our posterior, and that's how a Bayesian does prediction every single time. That goes from 0 to infinity, where that parameter lives. Just replace all this stuff, lambda to the x tilde, e to the minus lambda over x tilde factorial. I'm going to leave all these in so I can try to start recognizing what this distribution is. If I don't recognize the distribution and I don't know what it is, I don't just start throwing things away. So once I get comfortable with what it is and how to recognize it, then I might start throwing things away. And this thing is just our beta tilde alpha tilde over gamma alpha tilde. And I might leave it like this, just while I'm playing around with everything so that I can know where all these pieces have come from. And this is going to look like lambda to the alpha tilde minus 1, e to the minus beta tilde lambda. So that's what that thing looks like. And I just need to integrate that. We've already heard what distribution this is from somebody that knows way too much about stats. So somebody help us out again. What distribution is this? It is a negative binomial. So, and that's something you'll know after this. But if you take a problem like this, where the likelihood looks gamma and you integrate over a gamma, it's going to be this negative binomial thing, if those x's are discrete. We'll work through that. I need to tell you what a negative binomial actually looks like at first. So let's just do this real quickly. So a negative binomial distribution. Give you an example. In a second. Let's just imagine you're in the middle of a test and you get something like this, and you're like, uh-oh, I'm about to tame this problem. I forgot how to integrate, I'm getting all nervous. I don't know how much time this is gonna take. You could start telling me things about this distribution real quickly. So you might say, hey, I know that it's negative binomial, I'm gonna state that, at least. Won't get you all the way there with points, but that's at least good. You know that, you know what you're after. I think that's worth something. But you could probably tell me these. And you might think that this is a really hard problem because you don't know what the expectation of a negative binomial is off the top of your head. And working through it would require you to work through an infinite sum and know whatever trick there is to make that sum turn into something we recognize. And you never know in a nutshell if you can just do that real quickly, but we can still use our old iterative forms. This is a hierarchical model. All Bayesian models are hierarchical models. So this is going to be the expectation of x tilde given lambda and cap x, given cap x. So Bayesian is always conditioned on the data. So you'll always want to do that. This looked a little more complicated before, where we had a condition on sigma squared as well. This problem is simpler, there's just one parameter. What's that? That's lambda. Boom. Why? If I know lambda, the data doesn't help me, the data helps me to learn lambda in a prediction parameter. So because of everything the IID that falls out, you can leave it in there if you want, it's correct. But given lambda, that's no extra information. The expectation of x tilde given lambda is lambda because we know that the mean and the variance of the Poisson are both lambda. We saw that last time. So this is expectation of lambda given x. That's our posterior distribution. And this thing is just our alpha tilde over beta tilde. You can work out what that thing is if you wanted to. You can do the same thing with variance. They're not going to be exactly the same. Let's just do that. So the variance, lambda tilde given x. You might be thinking, oh, it's Poisson, so it's got to be the same, but you would have just made a mistake. It's not Poisson anymore. It's negative binomial. So this is equal to the variance of the expectation of x tilde given x. I'm going to condition on lambda. It's the only thing out there that I haven't conditioned on, so that's what we condition on. It gives us information. I'm going to add this to the expectation of the variance. X tilde given x, lambda given cap x. Again, that thing is lambda. Every single time this x is going to fall out because of conditional independence. This one still falls out. That's just lambda. And luckily for us, that's lambda as well. And so this is going to be the variance of lambda given x plus the expectation of lambda given x. This right here, we probably know that's alpha tilde over beta tilde squared. And this one right here is alpha tilde over beta tilde. So what does this look like? Alpha tilde over beta tilde times 1 plus 1 over beta tilde. What we notice is that this is bigger than that. So bigger than the mean, that feels pretty good because we know that every other counting distribution out there in the world that we can form through a mixture of Poissons is going to have higher variability. That's what the stochasticity does by averaging over something. And so that's our over-dispersion factor in this analysis. And that's the right over-dispersion factor. I can write those things down and write down exactly what those formulas are without having to memorize anything. So I will give you a heads up. I always forget what the negative binomial expectation is. I'm always like, does this shift from the left to the, where do I start counting? What is the parameterization of this? and I'm always slightly confused. So I always rewrite it, and that's what I do. So let me show you how to do this. So a negative binomial, just let's come up with an intuitive understanding of what the negative binomial is modeling in general. Not in terms of this problem. I don't actually use this as insight in this problem. It happens to be a negative binomial distribution that we get out of this integral. We'll see that in a moment. But sometimes when we take a probability class, people give us an understanding of a negative binomial from a different vantage point. I don't know if this will help you exactly with this problem, but it'll help you to remember what a negative binomial is. So what is a negative binomial?
It's the number of failures. So you're running Bernoulli trials. Bernoulli trials. It's the number of failures before you reach the gate success.
So if I'm flipping a coin, I'm going to define k, so maybe k is 5, and k is going to represent the fifth draw, the draw in which the fifth success occurs. Minus the successes out of there, minus 5 will give you the number of failures. So I can either model the total number of trials as random, which I just did in my mind, and then I shifted it and I subtracted it over to meet David's definition. So I did this little transform in my head. Let's see if we can try to find some way of remembering what this distribution actually looks like. I like this, this works for me. This is one way to remember. I could also call this the number of trials. Or trials. Remember, the trials is going to be the number of failures plus the number of successes. So k is the number of successes that we have, that's fixed. This is random. If I add something fixed to something random, that thing is random. So there's two ways to think about a negative binomial. You can either model the number of trials of the k success or the number of failures you saw before the k success. And those are just shifts by k. See if we can remember what this distribution is. I do this the same every single time. Come up with an example. Let's let k equal to 6. That's the number of successes. N is the number of trials. And what should we use for failures? I'm going to say y. And what we're thinking about is just heads or tails in a Bernoulli coin flip. So that's my success or failure, heads or tails. So you could call this heads. And this one tails. Okay, let's just look at an example. I'm going to say this is 10 right here because I just opened up 10 slots. And this is what maybe a negative binomial process would look like. We know that's a heads, that's a success, that's what stops everything. So this is going to be our 6th head, according to my example. This is just an example. And I know how many heads are in here. There's going to be 5 heads. And there's going to be how many failures? 4. It's the difference between those two things. I could have either defined that first, and that would have defined that, because k plus y is equal to n. That's their relationship. So 5 heads, 4 failures. So I got maybe a head here, 1, 2, 3, 4, 5. Tail, 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 tail. These could have happened in any order. We're probably would be a little suspicious if those were all heads, and then we saw a streak of tails. I'd probably start thinking if I saw data that looked like that, it might not be independent. So, but saying that, it could have happened. So this is under any random order of these things, and I've got n is equal to 9 in this block of things. So this is my new n, and I'll just call it n star. And n star is always n minus 1. The last thing right here is fixed to be a heads, if that's a negative binomial process. This happens with probability p. So that's the probability of this thing happening on that last independent Bernoulli trial. And this stuff right here has a distribution I'm entirely familiar with. This is binomially distributed. So what we know from this is there has to be n minus 1 fixed things in this block right here. Of those, I know exactly how many are heads and tails because I've stopped the process here. So we can write that down a number of different ways. Let's do that. So this is going to be p times, so p and this stuff happened, that's the times. So what do I got right here? I've got 9 choose, I'm going to say 4. I could have done that at 5 as well. And this is going to be p to the 5 times 1 minus p to the 4. That's the number of failures. And I can rewrite this thing and combine that one with this one. And this is going to look like p to the 6 times 1 minus p to the 4. And this is going to be 9 choose 4. And I can rewrite this. I could call this p to the, what was our letter? K. That's the number of successes. That was fixed. Not done writing. Times 1 minus p. That's to the y. That's the number of failures. What I called 4 before. That fails. And that's random. And then I got this thing right here. I could call this n minus 1 choose y if I wanted to. Or I could write this out as x plus y if you want, or k plus y. And that's what I've derived. So I kind of like to see the y's in here. If I'm calling that thing random, then I can code that as y. Right there. If I were treating the n as random, I would let that be n. And then I would probably write the number of successes down here. Success is minus 1. So I can rewrite this whole entire thing if I wanted to in terms of n. Just write that. That's the number of trials. That's also random. That's just k plus y. I can just rewrite this thing. This is going to be p to the k, 1 minus p to the n minus k. So I just rewrite everything in terms of n. And this is going to be n minus 1. And then I probably put my success successes down here. This would be k minus 1. Keep in mind what we counted over here. This was my k minus 1 heads. Right there. And that's how we derive that number in the first place. So that's a way of expressing this in terms of n. I usually try not to remember what the negative binomial formula is, but after a while, you just can't forget it. So does anybody know what it is for this parameterization? So I'm going to call this is going to be the probability distribution of y given k. If you want to write it down like that. I like doing that. But your book will probably end up just writing down probability as y. So, but I like to condition on k and remind myself what I did. So the expectation of y given k, what's that?
Sorry, where does the k minus 1 term come from in that choose? Okay, over on that.
This right here, I could have replaced this with a 5.
Yeah.
How about this?
Well, because it's y in that equation there, but then.
Y is here, exactly, but it's still the same.
Yeah.
Same number that I'm computing. I just want the y to be there when I start adding over it. So that's the same thing. I could have put the success as minus 1. I can either put this number in there, or I can put this number in there.
Okay.
They're the same things, right?
For the choose factor.
That's the, yeah, exactly. So if I n choose C, I'll say, I could end up doing this. Let's just rewrite this down. N choose C is equal to n factorial over C factorial over n minus 1 factorial. Yes, thank you. You guys are on me for that one. So everybody knows that one. So this is also equal to n choose n minus C.
So this is maybe mechanical, so I understand if you don't do it, but like you could have also written this another way where you flipped the definition of success and failure.
So
You get like the formula would be very different.
yeah, you also treated the wrong things random too.
Because the you could just say like you're just flipping definition of success and failure.
Yeah, but you're also changing what's random.
Oh, because it's fixed the number of successes.
Yes, that has to be. Now you have to change the problem completely.
I see. So that would be you would get something that's wrong if you did.
Yeah, there is a symmetry, and I bet you could fix it at the end, but you have to fix it. What's the expectation of this one? Anybody know? I'll write down the easy part.
K over n.
Has something to do with k. It's not k over n. The end. P over 1 minus p. So is it p over 1 minus p, or does it go the other way? Could you figure this out? Chris remembers it's one of these two things. It's either this or that thing in the braces is 1 minus p over p. So good memory, I bet you could untangle that. Remember, if this is the error probability, this has something to do with failures. If that's bigger, the failures should go up. This one, if that gets bigger downstairs, this thing goes down. But this is the expected number of things. So if I put more probability on the failures, this number should be climbing. So that's the way I remind myself which way it goes. So 1 minus p over p. Again, this is hard to remember, and I'm not going to hold you responsible for knowing that. So it's not a bad thing to know when you see negative binomials. I remember this one. If I were to reparameterize this thing, this is the probability of n given k. It's a little bit different Y here is going to go from 0, 1, 2, 3, all the way up to infinity. So those are the number of failures that could happen. I could have seen success, 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 success k times, which would mean there's 0 failures. Or I could end up writing this down in terms of the number of trials. And I bet you could use this formula over here to derive what this is. I'm going to write down the wrong thing. How do I fix this answer? Subtract 1. Subtract y. Why would this not make any sense? You can't even have y in this equation because you've integrated y out. That's the definition of an expectation. An expectation for something is always going to have something to do with the fixed stuff. They're always functions of what you're conditioning on. Y is the random variable, which is akin to this. This is just going to be k plus y. So that's kind of like talking about n, which is the random component. So not that. Where does n go from number of trials? So if I had a process that was success, 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 success k times, then the number of trials has to be bounded by that number of successes.
K plus 1.
You guys do. K plus 1 plus so it starts there. It's just a shift. Shift. Okay. Has something to do with the number of successes you've seen. And this ratio is hard to forget once you realize the failure probability has to go upstairs and make this thing bigger. So I remember that, and then if somebody has me with this parameterization, I can jump to that. It won't help you in this problem. It's not the way I think you should untangle what the mean and the variance is. I think you should use the hierarchical forms. Let's convince ourselves that this distribution is negative binomial. So I'm just going to keep these things written up on the board. And I'm going to do some integrating. If I need help with this, I'm going to need help with our integrals. So let's concentrate for a minute. X tilde, I can call this probability if you want. I just like to remind myself it's a posterior distribution, but this is a probability statement. So if you prefer to call that a probability, go ahead. This is going to be equal to the integral from 0 to infinity. We'll just write this out again. Probability of x tilde given lambda, pi lambda given x. D lambda. I'll just write down what that sampling distribution looks like. This is e to the minus lambda, lambda to the x tilde, over x tilde factorial. Do not throw that away. So this is a time where you can't get rid of that. That's part of the distribution. So it changes the whole shape of the distribution. That's our sampling distribution. And then this one is a gamma. And I'll write it down in its full-blown glory. I'll use some notation that we've developed. Gamma alpha tilde, and I'll try to remind myself what these numbers are in a second. So this looks like lambda to the alpha tilde minus 1, e to the minus beta tilde n. All through college, I was training myself to not drop terms, or if I got confused in my math, I could always back up and see where I got everything from. Start throwing all the xi's in here, it might be difficult to see where you go wrong. So I'm going to leave it like that, and I'm going to remind myself that alpha tilde is sum of the xi's plus alpha, that's my original hyperparameter, I could set it equal to 0 right now, but I'll just leave it there for the time being. It's a low widget, and I always bury these into my code as well. So if I want to change the prior, I can do it real quickly in my code.
So your prior is, yeah.
I'm just going to finish writing this down so I don't forget.
So you can do, when you do a mixture of like a discrete distribution and a continuous distribution, the resulting distribution is always continuous.
How is this continuous?
Because you have an integral.
I'm integrating over this,
Oh, okay.
but that's discrete.
That's discrete.
So here would be a counterexample.
Okay.
So just make sure you treat the continuous stuff as continuous all the way through, and the discrete stuff as discrete. Let's just do some factorizing. I'm not going to start throwing all this stuff away because I don't know exactly what it all means, and it might help me to recognize the distribution. If you're really savvy at recognizing what negative binomials are, just start chucking stuff. So, but I need to look at it. So I can factorize that stuff out right there. This is lambda. Yes. So I changed that. Very good. So this is going to be beta tilde alpha tilde over gamma alpha. I can pull this out right here. This is going to be lambda tilde factorial. And then I've got this big interval. This is going to look like e to the minus lambda. And I'm going to get this one right here. So I'm going to combine these. So I've got this one plus that stuff. So I'll write beta tilde plus 1 right in there. So this is lambda. This is going to go alpha tilde plus x tilde minus 1. So that's just these two terms. D lambda. 0 to infinity. I might start thinking about at this point, what was beta tilde again? And I would do a sanity check that this all makes sense. We'll do that in a second. So, just real quickly, what is this integral? Kernel of the gamma. So, I'm going to call this maybe alpha star. And this one I might call beta star. Right there. So what's this integral equal to?
Beta star, negative alpha star.
Beta star to the minus alpha star. Gamma alpha star. And there's our answer. Let's try to recognize it. Don't want to lose too much room here. Do it over here. So let's just start replacing numbers right here. This is beta tilde. So this is n plus beta raised to the alpha tilde. That's sum of the xi's plus alpha. Right there. I'll do my gamma alpha tilde. That's sum of the xi's plus alpha by original hyperparameter. There's an x tilde factorial here. And then I've got all this other stuff. This is going to be beta star. So what's beta star? Beta star is beta tilde plus 1 raised to the alpha tilde and alpha star to the minus alpha star. So this is minus alpha tilde plus x tilde. That's that stuff. And then I got that stuff. So times gamma, alpha star is alpha tilde. Whoops. Alpha star is alpha tilde plus x tilde. And I can rewrite this by reminding myself what beta tilde is. So let's just do that. N plus beta raised to the sum of the xi's plus alpha. alpha over gamma, sum of the xi's plus alpha, x tilde factorial. And this right here is beta plus n plus 1. This is going to be minus sum of the xi's, bless you, plus x tilde plus alpha. This is alpha tilde is the sum of the xi's plus alpha, but I want them to just tuck those right next to each other. And it's starting to look pretty good. Where did that n come, that 1 come from? That's the predicted distributions count. That's your sampling count. And they show up right next to each other. And no great surprise, we saw that n plus 1 show up thing in our other prediction. And then I've got this last bit times. This is just a gamma. So gamma function times sum of the xi's plus alpha. Is this right? No.
Because it's sum of the xi plus alpha tilde.
Right. So that's alpha star right there. So this is alpha tilde, this is this stuff right here. Alpha tilde plus x tilde. This is sum of the xi's plus alpha, right there. Now we need to wiggle this thing into shape. And I think we can do that. Yeah, I think I can see it. I'm ready to get rid of this. I think we got this all correct. If I got rid of this and it's not correct, I'll never be able to fix this. I think it's right. This, I'm going to just do some combination of things. So this is gamma, sum of the xi's plus alpha, I'll put it here, plus x tilde plus alpha. This is over sum of the xi's plus alpha. So I have 2 of those. And then I've got an x tilde factorial down here. So that's my normalizing constant. And I'm going to combine these 2 terms right here. So let me just do this. I'm going to raise one of these to the sum of the xi's plus alpha. That's the xi's right there. And I'm going to have a part that has the x tilde in here. This is going to be n plus beta over n plus beta plus 1. And this is going to be 1 over n plus beta plus 1. So I factorize this thing apart into a product of this thing and that thing, and another one raised to the x tilde. And I threw those downstairs because of the negative sign, and I combined the 2 things that have the sum of the xi plus alpha together. So this is the negative one. So if I ended up picking alpha to be something that's non-integer, I would leave it in this form. If alpha was an integer, so let's say it was 0 or something like this, I could re-express this as a factorial. That's a factorial. That's a factorial already. And so this would look like your binomial coefficient. A typical coefficient you see. So you can rewrite all this. So again, if alpha is an integer, this thing is going to be sum of the xi's plus x tilde plus alpha minus 1 factorial. There's going to be a similar factorial here. It'll look like this. Sum of the xi's plus alpha minus 1 factorial. You can combine all those terms, and you can match them to this formula right here. And they're the same. And you could use all of that stuff replace all your notation and rework the expectation if you want, and they will match. They'll be right. If you just pattern match everything in there, to everything up there, and plug into the formula here. I would never do that, because I would guarantee to make a mistake on a test. So I just do the hierarchical thing, work out the expectation of the variance. Because that sort of metaphor of how many successes or failures I see before the case success doesn't really apply to this example. That's just a way I remember what the negative binomial is. So I'm going to present a problem like this to you on the midterm. I'm going to pick some distribution. I'm going to ask you to do the inference, and I'm going to ask you to do the posterior predictive distribution. I'm going to ask you to recognize the mean and the variance. You've got a template for doing that. All you have to do is anticipate what my distribution is. You probably want to know what is the expectation of the variance of it. If I asked you to do it on an exponential distribution, you might know the relationship between an exponential and a gamma. I wouldn't even need to tell you. You just recognize the exponential and go, oh, that's some gamma. You would tell me which gamma it is. And you would start working with those forms. So I did that last semester. That's how I taught it. So I always pick a new distribution and I make sure that you know all the little tricks. It's just a way to make you memorize distributions and their properties. I think tomorrow or on Wednesday when we come back, I'm going to kick off an introductory lecture to MCMC just to get us thinking about it. And when we come back from break, we'll learn all the details. If you want to get started on my motivating example, it's listed under the paper that's titled Gelfand-Smith on the webpage. It's the thing right before the tentative statement. So have a look at that. That's it, you guys. Thanks so much. I was hoping you would